Hello everyone. So this video I'm going to cover inductors, the fundamentals of inductors, and let's just hop right into it right away and let's look into what inductors are. So inductors, the fundamentals. So we had spoken about capacitors in a previous video and saw that they're basically two plates. They're an energy storing device, and physically it can make sense. Inductors are a little more bizarre, and we're not going to go into all the details of it. They are heavily affected by magnetic fields, or because they produce a magnetic field, and how the current in the wire produces the magnetic field and how that magnetic field affects a wire that's close to it is what makes inductors very, very interesting, has lots of applications, but also makes it fairly difficult to fully understand and calculate. We're going to keep it really basic and simple. And in the most part of what I'm going to say and what we're going to show, it works, especially in DC. There's a lot of gray area in inductors and a lot of little, if I can call them, exceptions to what I'm going to say. But in general, what I'm about to say works in DC, and definitely on paper, it works out. What happens after, we'll worry about that in the AC circuits class. Okay, so in essence, an inductor is a really long insulated, this is important, I'll explain why that's important. So it's a really long insulated wire that is coiled up around a material. Okay, so in essence, it looks something like this, right? Where there's a material that is in the middle here, going through the coils, okay? How tightly the coils are brought together affects the value of the inductor. What material is in there affects the inductor, the value of the inductor. This material is often something we call, now I'm forgetting the name of it, a ferrite. This material is often a ferrite material. In essence, it has iron in it and is affected by magnetic fields. It doesn't have to be this. That's why I'm saying it's often. Air can also be the material in an inductor. Okay. It has different properties, but will still produce the inductance that we're expecting. Okay. Fundamentally, all we need to worry about is that it's a really long wire that's coiled up, and as current flows through it, we know, and if you don't know, it produces a magnetic field using the right-hand rule. Okay, my thumb is pointing in the direction of the current, and my fingers wrap around the wire, wrap around the current to show me the direction of the magnetic field. We don't care about that. We just know that when all that happens, we get an inductor. That's all that's important to us. Okay, so I can give like a really fancy term, okay? It's called self-inductance. And this is the measure of a coil, and sometimes an inductor is referred to as a coil. So the measure of a coil's ability to establish an induced voltage. So basically across its terminals, so across the inductor, we can produce a voltage as a result of a change in its current. Okay, so there's definitely a relationship between voltage and current and inductance, or the inductor. Okay, again, like I could throw in this equation, and so the voltage, that induced voltage, is equal to L, and L is your inductance times the derivative of the current as a function of time. We don't care. We're not going into the calculus. We're not looking at any of this. We're just going to be using some concepts that help us in DC, all right? But this is where it comes from. The unit for inductance is henries. And I'm not sure why I put a capital H, because it's not a name, or it's not, I mean, it's based on a name, but it's not a name. So henries, H, right? So millihenries, kilohenries. I usually don't have kilohenries, but millihenries, henries, microhenries occasionally is sort of typical ranges for inductances. All right. And the schematic or circuit symbol, I've already kind of drew it. It kind of looks like a resistor, except we make a little curly to represent the coils. And so that's our inductor. It's in henries, and you could see different from voltage, different from capacitance. It's the current that's really the key in looking at inductors and how they function and how they work and what they do and all that. Now, there's a whole study on, how many turns, how many coils you make, how tight they are, how close they are, how far apart they are. It tells you how to calculate the value of L. We ain't doing that. We don't care. At this point, we just care that we have an inductor and it has a value. And that's pretty much all we worry about. Little note, because I didn't really say it, an inductor is an energy storing device. But practically speaking, it doesn't function at all like a capacitor, really, honestly. Like a capacitor, I could pull it out of the circuit and it holds a charge, and I could plug it in somewhere and it discharges. An inductor doesn't really work that way, okay? If you've ever used a power tool, I don't know if anyone's ever used a power tool, especially a drill, and you run it and you kind of look in the little cracks, like the air vents essentially, and you watch it and you kind of let go, you'll see sparks inside, okay? And that's really, there's an inductor in there, and that's what happens practically, is like it can't really store energy, so it's got to get rid of it, and that's why you kind of see a spark, okay? On paper, and using a function generator with a square wave, which we saw in the PBL, or hopefully we saw in the PBL, people are working on it, okay? When it's high, it's like on, and then when it's low, it's like off, and the circuit charges when it's on and discharges when it's off. And with an inductor, we can watch that. We can see that relationship in an inductor as well, okay? But when we put a battery, it doesn't quite work the same. So that's an aside. We're going to pretend you didn't hear me say that, which, by all accounts, most people don't listen to what I say anyway. So it's all good. That was supposed to be a joke. Okay. Steeped in some truth. But anyway, so this is what an inductor is. Now, let's look at what it does when they are in series and in parallel so that we have an idea of what things are going on. So it's kind of like the capacitors as well. So L inductors in series. So as an example, we got a bunch of inductors in series. So L1, L2, Ln, doesn't matter how many they are. And so L total or L equivalent is L1 plus L2 plus however many inductors we have, right? Just like a resistor, just like resistors in series or capacitors in parallel, if you remember. And then inductors in parallel, can you guess what it's going to be like? And if you guessed that it'll be like resistors in parallel, you are absolutely correct. And so L total is equal to 1 over L1 plus 1 over L2. These are L's plus however many you have, Ln, all inversed to the minus 1. Again, just like resistors in parallel. Now, if you have a hard time remembering capacitors and inductors, how they get added up when they're in series and parallel, I still remember this. My friend came up with this back in university, and I mean, I didn't need this tool, this way of figuring it out. But you know, if it helps, great. You know, so inductors we add up exactly like resistors because they kind of look like resistors, right? Resistor is the squiggly line, an inductor is the curly line, and your cap is two straight lines. So the capacitor is completely different. So the capacitor is opposite to these two. So when they're in series, we add them up if they're resistors or inductors, obviously not together because they're two different devices. But if I have inductors in series, resistors in series, they get added up. When they're in parallel, we do the 1 over thing. Capacitors are the opposite. When capacitors are in series, we do the 1 over thing, the 1 over C1 plus 1 over C2, et cetera, all inversed. And when they're in parallel, we add them up. So again, resistors and inductors, because they kind of look the same as in the schematic pictures, they get added up the same way. All right. So that's pretty standard, pretty straightforward. Before I go into the full charging and discharging thing, I do want to mention how an inductor behaves in DC. All right. So at the start or initially or when the circuit is turned on. If we remember, the capacitor acts like a short circuit because it wants to quickly move the charge out of the way and balance out, you know, the voltage across the capacitor. And so it starts at 0, but acts like a short circuit, and you know, all the current flows, all the electrons flow until we come to a stop at the steady state. Okay, keyword. So after a long time, and we can't add any more electrons on the plate, then it acts like an open circuit. An inductor is slightly different. And because it's a super long wire, right at the start, the inductor acts like an open. So VL is at max, and IL equals 0. Right at the beginning. Literally a split second later, it's all gone. It's an equation that we're going to see, which looks exactly like the equations for capacitors and the voltage, okay, for charging and discharging. They look exactly the same. We're just looking at a different quantity. It's not voltage, but current. All right. But right at that beginning, your VL is max because it's an open, and your IL is 0. And you have to sort of figure out what that max voltage is. Now stop and think of it this way. Think of an inductor as, or one end of the inductor as a red light. And you've got cars lined up, 30 cars back. And you're the 30th car, you're at the back. When the light turns green, i.e. the circuit gets turned on, do you move? If you're the 30th car, no. You do not move at all. You do not notice. The car in the front may start going, okay? But you do not move because there's cars in front of you. You can't move. So it's not exactly how it works, but at least that illustration kind of shows you. Just remember, you're not the first car in line, because the first car in line, light turns on, you go. All right, so it doesn't look like an open. Think of it as the last car, that when the circuit turns on, that car does not move. Okay, so that's the same thing in the inductor. Because it's a super long wire, the electrons do not move instantly, right away. 1 second later, yes, or not 1 second later, but like, a nanosecond later, they start moving. And we're going to see the equation in the next video. But right at the beginning, it's like we can't move yet. So it's like that traffic light, all right? At the end, or at full charge, if I can call it that, or at steady state. So these all mean the same thing. And remember, steady state is approximately equal to 5 tau. If you guys remember that, we'll talk about tau in the next video as well for inductor circuits, right? At this point, it's a wire. So a wire I didn't leave myself enough space. So at this point, L is just a wire. So IL equals max current, because it's like a, what's it called? A wire. And your VL is 0 volts because it's essentially a short circuit. It's a wire. A wire or a short just brings 2 points to the same potential. So now the potential difference across the inductor at steady state only is 0 volts. Okay, so if there was anything important to remember for capacitors and inductors, it's this idea. Okay, so the inductor, right at the start, that initial, right when the switch turns on, VL is max and IL is 0, because the inductor acts like an open. The opposite is true for the capacitor. Right at the start, it acts like a short circuit. So the V capacitance is 0, and I capacitor is max, whatever that ends up being. And then at steady state, after a long time, after we've waited it, after we've fully charged or discharged, okay, the inductor is just a wire. So the IL will be its max and the VL will be 0. Opposite is true for capacitor. After a very long time, no more charge can be added to the capacitor. So it acts like an open circuit. And so your VC is the maximum voltage and your IC is basically 0. So I hope that helps. I hope it's clear. Do some problems and I'll see you in the next video.